Silicates. They are the minerals they contain SiO4 4 minus 4 units. They are linked together. They are linked together, and these silicates can be classified as orthosilicate, pyrosilicates, cyclic or ring silicates, then we have chain silicates, double chain silicates, sheet silicates, three-dimensional silicates, then zeolites. Now let us talk about the orthosilicates. The orthosilicate can be simply represented as, actually it's a tetrahedral structure. TH means tetrahedral, no doubt, tetrahedral. So you got the silicon at the center and 4 oxygen atom in this way. So here the dot represents silica, silicon. O represents oxygen. That is why we put this SiO4 4 minus. And this can be represented as, for example, you can simply put a triangle and at the center you can do like this. You have got silica. The dot represents silica, round represents oxygen. So you can link like this, as though that is you are looking from here. Okay, when you look from top, you will have the silicon at the center, O enveloping, and at the triangular position you can find oxygen like this. So this is a simple way of representing orthosilicate. Got it? Then pyrosilicate. So what is the formula of orthosilicate? That is SiO4. As I already told you, it's a tetrahedral structure. SiO4 4 minus. Example, beryllium silicate, Be SiO4. Beryllium silicate, Be2 SiO4. and pyrosilicate. The pyrosilicate will be like this. You can draw like this. Okay, put a line and round, round, round. Then you can have another round at the top, at the bottom like this, in between, and make it as a triangle, and this is also a triangle. Now at the center you have got a dot, that is silica. At the center you have got a dot, that is silica. Now connect this. That's all. So this is called pyrosilicate, a double silicate. It is also called the sorosilicate, also known as sorosilicate. So when you combine these SiO4 plus SiO4 and one oxygen being common, that is removed, so you are able to get Si2O7, because one is common. It's not a reaction, it's a simple representation. So what is the formula? This is nothing but Si2O7, and since you are lost one oxygen, so -2 will go. So overall charge is -6. Got it? If it is SiO4, 2 into -4, -8, you are lost one oxygen, so -2, so -6. So Si2O7 -6 is the resultant. You understand? So this is called pyrosilicate. So here, by joining these two orthosilicates, you are able to get the pyrosilicate. Got it? And the example is thottwitite, that is scandium silicate, scandium pyrosilicate. Now let us move to the tetrahedral structure. Now we move from that and it forms a simple cyclic structure, that is ring structure. So cyclic silicate. Cyclic silicate means, that is, you can draw a triangle like this and round, 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 and another round, another round, another round. Now form one silicate here and form, and this is the silica around which you have got oxygen. So link this. Similarly, you have got another triangle, another triangle. Here you can put silica, silica, round, oxygen, oxygen. So link this. That's all. Are you able to follow? So 3 tetrahedral forms a triangle like this. So this is known as cyclic silicate. It forms a cyclic structure, is it not? Or ring silicate. So here SiO 3 n number of times, and for every n there will be a loss of 2n. So these are the general formula. Similarly, this cyclic can further be developed, and you can draw like this. Draw a hexagon, a benzene like structure. Okay, hexagon. and at each point put dot round, dot round, dot round. What does dot represent here? Silicon. Dot round. Round represent oxygen. Okay. And then you can have oxygen here in between. Oxygen, 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 oxygen. Okay. Now at each terminal you can have one more oxygen. It should be at the equivalent position like this, and put a bond. Oxygen, oxygen, oxygen. So you can enjoy like drawing column. Pulley column. Now you can join. Right? Okay. So this is one tetrahedral silicate, another tetrahedral silicate, another tetrahedral silicate, another tetrahedral silicate, another tetrahedral silicate. It forms a beautiful crystal like this. You like it? Nice? A fantastic pattern. So this is also a cyclic silicate. And then sometimes it can form a chain silicate like a pyroxene. You can draw a line and draw triangle based on this 1, 2, third oxygen, fourth oxygen, fifth oxygen, and above that you have got one oxygen, below that another oxygen, above that in the same line. If you want, you can have a dotted line like this, so that you can maintain. Okay, so in between that, here and here, on alternate position you can draw like this. Okay, and what you can do, form a triangle, form a triangle, form a triangle, form a triangle, right? So it forms a zigzag structure like this, and at the center you have got silica. So here one tetrahedral structure of orthosilicate, and join with the another orthosilicate, so that it forms pyrosilicate, and several pyrosilicate can join together to form pyroxene. Are you able to follow now? Okay, so you can continue like this. Done. So this is called, since it forms a chain, so it's called a chain silicate. So here this SiO3, it is n times combined. If it is n time combined, and for every n there is a loss of 1 to n minus, so you have to put 2n minus. So n represents n number of SiO4 unit. N represents number of SiO4 4 minus units. Are you able to follow? That is tetrahedral units, silicate tetrahedral units. N represents silicate tetrahedral units. You have to count 1, 2, 3, 4, 5. So if it is 5, and you have to put 10n here. Got it? And then structure of double chain silicates. Like in the case of asbestos, it is fibrous. So fibrous silicates. It's called double chain silicates. Okay, so you can form a structure like this. Draw a benzene like structure. Another benzene adjoined to this, similar to benzene, double benzene adjoined, and another benzene can be joined. Okay, now as I already told you, you can put dot here. Okay, another dot and a round, another dot, round, another dot, round at each vertex. Okay, right. Now you can further draw the just extend here, not here. And put oxygen. Okay, and in between you have to put oxygen. Right. Now at each corner you can have the tetrahedral structure. Are you able to follow? You can join like this. Okay. Done. So you are able to get a very nice structure, double silicate, that is double chain silicate. The best example is asbestos. These double chain silicates, they are also called amphiboles. They contain Si4, O11, n number of silicates and 6n minus. Got it? Here you can find the two types of that is tetrahedra. One is those sharing three vertices, whereas here they share two vertices. Likewise, two types, and that's why it's called amphiboles. Then you can develop sheet silicates. The sheet silicate can be drawn like this. The same benzene like hexagon network. Okay. Now what you are supposed to do? Take the vertices with the silicon and oxygen, silicon and oxygen, silicon and oxygen. You should have patience to draw such type of structures. So once you are able to understand the pattern, you can do it very easily. It may look so complicated, but when you start drawing it, it's so easy. Okay, have you finished this silicon and oxygen? We are done. And then now in between that, oxygen, 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 round, round, oxygen, 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 oxygen. So simply draw in between oxygen. Okay. Right, and at each apex vertex you can have one oxygen, and make sure that these are equidistant so that you can form a triangle here. Okay, don't put here, it is already formed. Don't put here. First you link all these things so that you can be sure about the structures. Right. Now, okay. Okay. It forms a very beautiful pattern. Done. I think I almost completed. So it forms a fantastic sheet like silicates, and this talcum powder, face powder, it will be having such a beautiful structure. Mica is also having such type of structures. So it forms several layers, and that is why it forms a sheet pattern. And such type of, in fact, coating having such type of material will be highly water repellent. So micaceous coating we used to say, highly glossy also. And even talcum powder, it consists of this type of material, silicate. It's only, say, Tamil mannan solla, manna thiki posikala. But it's a special type of silicates, that's all. Okay? And that's why It has got some luster also. Artificial pearl, it is made up of such type of material. Micaceous one. Okay. Yeah, what do you want? Done. And this is called the sheet silicate. Examples, and is also called the phyllosilicate. They contain the structure Si2O5, n number of ions with 2n number of minus ions, where n is equal to, as usual, SiO4 4 minus tetrahedron, where n is equal to each n. Okay, each n represents one SiO4 tetrahedron units with the tetravalent ions. They stack over each other and forms a beautiful sheet-like network. And they are held together by weak van der Waals force. These sheets, they are, let me represent each sheet like this. One sheet, another sheet like this, with a lot of, that is a star pattern like this, and in between that you have got van der Waals force of attraction. A weak force of attraction, and they can be readily cleaved also, being a weak force of attraction. And with that we have another type of sheet, silicate, that is called three-dimensional silicate. It's called a Tectosilicate, 3D silicate. Also called Tectosilicates. They are much more complicated because three-dimensional, and they have the common structure Si2O5 n number of units with 2n number of charges, minus charges. Three-dimensional is SiO4 with 4 minus. They combine with this and forms, they have the general formula, this is tetrahedron unit, and they have the common SiO2 n number of times. Example, quartz crystals. Spadigamnu solralla. This quartz has got some speciality. When you pass current, it will start vibrating. When you mechanically vibrate, it will give current. That is called piezoelectricity. And that is a crystal which is embedded in the watches, and that is why it's called quartz watches. Piezoelectricity. The current obtained by vibrating the quartz is called piezoelectricity. Piezo current, you can say. And we have much more three-dimensional silicates. They can be called zeolites. They contain, along with the silicate, aluminium, silicon, and oxygen. Their general formula is sodium oxide, and along with that you have got alumina, Al2O3, aluminum oxide. Then it may contain X number of SiO2, silica, and with the Y number of H2O, hydrate, where these X may range from 2 to 10, Y may range from 2 to 6. The speciality of zeolite is they have porosity, pores. Pores means a lot of small holes, where sodium ions are Na plus ions and water molecules, they are held in pores. In fact, they are loosely held. And the silicon, aluminum are connected tetrahedrally. Silicon and aluminum connected tetrahedrally. Through oxygen, shared oxygen. Zeolite act as molecular sieves. Like a filtration unit. They can remove permanent hardness. Of water. Hardness of water means what? The presence of salts like carbonates, chlorides, sulfates, they will cause poor lathering of soap. There are two types of hardness. One is temporary hardness, another is permanent hardness. Some salts can be easily evaporated, some salts cannot be so easily evaporated, like calcium chloride or calcium sulfate. In such case, those salts present in water which cause permanent hardness, by using this zeolite filtration. Okay, when it is passed through this zeolite, the water is trapped, that is the molecules present in this, like a calcium, silicate, all these things, sulfate, they will be trapped inside these zeolites, and thereby you can remove those salts, thereby that water is free from such hardness, that is permanent hardness, so that you can have better lathering and better taste also. Okay, so this is the way we can make use of this wonderful salt, silicate. Okay, so far we have discussed several types of silicates. Okay.